Okay, we're actually going to cover something today in much greater detail than we do when we cover it in 242. So we actually covered this section more or less in 242 when we're talking about approximate integration. But today we're going to we're going to go through like what we did last time to get everything today. Okay, so we talked about interpolating polynomials last time. We're going to use those interpolating polynomials today to develop integration formula for numerical integration of functions. So how do we tell a computer how to integrate a function accurately? So in 242 or 241, you probably covered left endpoints, right endpoints, Riemann sums, midpoints, stuff like that. And you could use those to approximate the value of your integral. Today, we're going to use interpolating polynomials to interpolate our function and then integrate the interpolating polynomial instead of our function. Okay, does that make sense? So today we develop approximations for integral from a to b f of x dx by approximating f of x with interpolating polynomials. So that's basically what we're going to do today. We're going to interpolate our function, integrate that interpolation, and say that's the approximate value of our integral. Okay, does that make sense? So let's look at the first type of function we could use to approximate our function. So the first type is we can interpolate by using a linear interpolating function. So can use number one, linear interpolation. So the first part is called a single trapezoid rule. Single trapezoid rule. So I have some function over some interval AB and let's say my function is something like this. So this is my f of x. And I want to integrate this function over the interval AB. Okay. So we want to compute the integral from a to b f of x dx. That's what we're after today. Integral over some interval f of x dx. Now, what I could do is I could take this function value and this function value, interpolate with a straight line, and integrate under that straight line. Okay? So the straight line connecting these 2 points, what is that? It's P1 of x equals f of xa, or sorry, f of a plus f of b minus f of a over b minus a times x minus a. That's the linear interpolating polynomial passing through those 2 points. Does that make sense? We talked about that last time. We derived this Newton interpolating polynomial last time. I have b1 and b2 right there. I have my first two b values from my Newton's divided differences right there in my linear interpolating polynomial. We talked about all of this stuff on Thursday. So this is my linear interpolating polynomial. This is the line equation that passes through these 2 points, a comma f of a, b comma f of b. Does that make sense? So now, instead of integrating our function f of x, I could just integrate this line from a to b and say that's approximately the value of my interval. Okay, so at this point, I can say that this integral is approximately integral from a to b, p1 of x dx. So that's going to be the integral from a to b. Oh, I forgot to record. Am I recording? Yes. Oh. Ah, okay. So plug this function in. So we got f of a plus f of b minus f of a over b minus a times x minus a dx. How do I integrate f of a from a to b? Well, it's a constant multiplied by x, right? So this is going to be f of a times b, f of a times b minus a plus f of b minus f of a over b minus a times x minus a squared over 2 from a to b. Right, x minus a dx, I could do a little u sub for x minus a. So basically u squared over 2. So that means x minus a squared over 2 from a to b. The constant, basically the slope is just a constant. So I just keep that constant outside of the parentheses there. I could pull that out of the integral. So plug this in. This is going to be f of b times b minus a plus f of b minus f of a over b minus a times b minus a squared over 2. If I plug in a to that evaluation, I get 0 squared. Right? So I don't have to really think about the rest. I just have to do b minus a squared over 2 minus 0. Yes, sir. Yeah. Keep dropping that f of a. F of a times b minus a. Thank you. Times b minus a. Exactly. All right, so now I can simplify a little bit. This b minus a cancels with this square. And what can I do? I can factor out b minus a, right? So I can say this is b minus a times f of a plus f of b minus f of a over 2. Okay, does everybody follow? The algebra and the calculus, I guess. Okay. Now I can just combine inside the parentheses, find the common denominator of 2 for this f of a. Combine them. This is going to give me b minus a over 2 times f of b, or f of a plus f of b. So this is called the single trapezoid rule. I'm using a single trapezoid area to approximate the area under my curve. So this is a single trapezoid rule. I'm using a single trapezoid. Basically just interpolating a linear interpolating function to approximate my f of x over the interval AB. Sometimes this does a great job, sometimes this does a horrible job. Like if you had a parabola opening down and you approximated the endpoints, you'd be missing all that part above the straight line. So here, it's a decent line, right? And the graph that I showed, it'd be a decent job of approximating, but in general, it's not going to do a great job. All right, questions? How can we improve this? Well, we could cut up our x-axis into a bunch of little pieces and use a linear interpolating polynomial over each little piece. And that would give us a bunch of trapezoids, just like we did in Riemann sums. We could get the sum of a bunch of trapezoid areas, and that would be a better approximation. So that's part B, is a composite trapezoid rule. So part B says the composite trapezoid rule. So the composite trapezoid rule says take your function, f of x, over the interval AB, and cut it up into a bunch of little pieces. And interpolate linearly over each little subinterval. So we use a different interpolating polynomial over each subinterval. And we can see here it's doing a pretty good job of approximating our function. So we use a linear interpolating function over each subinterval. We call it x0, x1, x2, x3, xn is the very last term. And the spacing here between these is delta x. So the spacing between these consecutive points in the subintervals is a spacing of delta x. So that distance is delta x. So delta x is going to be equal to b minus a over n. N is the number of subintervals, or the number of trapezoids that you're going to use. Because each time you create a subinterval, you're going to interpolate the two endpoints of your function at that xi plus 1. You create a straight line, that creates a trapezoid over that subinterval. You'll find the area of that trapezoid, add them all together. So that's delta x. xi is equal to x0 plus I delta x. Basically, each time to get to the next x value, you're going to add delta x. So you just add delta x to get to the next xi value. So you're going to add it I times to get to xi. You add it 0 times to get to x0. Add it 1 time to get to x1. Add delta x 2 times to get to x2, etc. Okay? So let's look at just one subinterval. So focus on the interval xi to xi plus 1. So the integral from xi to xi plus 1 f of x dx is going to be approximately delta x over 2 times f of xi plus f of xi plus 1 by what we just did. Right? If we use a single trapezoid or a single interpolating function over one interval, this is the formula. Right? That's what we just derived. A single linear interpolating function over one interval is exactly this formula. Delta x is the difference of the endpoints, xi plus 1 minus xi, over 2 times f of xi plus f of xi plus 1 is exactly that formula we just derived. Except we called it b minus a over 2 f of a plus f of b. Well, now we're looking at one small interval, xi to xi plus 1. So the difference, xi plus 1 minus xi, that's delta x. And then f of xi plus f of xi plus 1. That's f of a plus f of b for this small interval. Does that make sense? So then the total area would be the sum of each little subinterval's area. So then, integral from a to b f of x dx would be approximately the summation, or actually let me just write it out, delta x over 2 f of x0 plus f of x1. That's the interval x0 to x1 plus delta x over 2 f of x1 plus f of x2 plus, so this is the interval x1 to x2, delta x over 2 f of x2 plus f of x3, and that's the interval x2 to x3. Plus delta x over 2 f of x n minus 1 plus f of x n. So basically I'm adding the area under each linear interpolating function over consecutive subintervals. Okay, does that make sense? So what happens is we can actually factor out delta x over 2. And that will leave us with f of x0 plus 2 times f of x1 plus 2 times f of x2 plus 2 times f of x n minus 1 plus f of x n. And that is the composite trapezoid rule. So if you want to remember that one, that's fine. But I'm going to write it in a different way. For our programming purposes, delta x over 2 equals f of x0 plus 2 times the summation I equals 1 to n minus 1 f of xi plus f of xn. And that's the composite trapezoid rule. So this will give us a way to numerically integrate a function over some interval AB. So let's look at an example. why is this useful? We didn't even motivate this. We were just like, let's do cool stuff. We didn't even motivate it. I mean, cool, maybe not enough motivation for everybody. Who is okay with us just doing this just because we like integration so much? Okay, we got a few hands. Yeah, that's cool. Integration's like the coolest thing in math. So that's cool. But, I mean, why would we want to do something like this? Why would we need to numerically integrate a function? Awesome. So we can tell, like, that's a very good, actually a very good answer. So we can tell the computer how to do it. That's a great answer. So we can tell the computer how to do it. That's a very good answer. But why would we want the computer to do it if we could do it? So there are some functions you can't do by hand with the fundamental theorem of calculus part 2, if you forgot which part of it. Basically, the fundamental theorem of calculus part 2 said the integral from a to b of f prime of x dx was equal to f of b minus f of a. So you just found the antiderivative, plugged in the upper bound, minus the antiderivative evaluated at the lower bound. That was the fundamental theorem of calculus. However, not every function has an antiderivative. So not every function has an antiderivative. So you can't always just do this f of b minus f of a thing. Okay. For example, let's look at our example that we might maybe want to do. Example, approximate integral from, we'll say 0 to 2, e to the negative x squared dx using trapezoid rule with n equals 4. So as soon as I say n equals 4, that automatically means it's a composite trapezoid rule. Otherwise, we would assume it's a single trapezoid rule. Let me detangle my cord 1 second. Okay. So does that make sense? This function, e to the negative x squared, has no antiderivative. There's no antiderivative for e to the negative x squared. That's a non-elementary function. We call it the error function, but it's really just made up of a bunch of numerical integrations, right? This antiderivative is actually made up from a bunch of numerical integrations. So solution, what we're going to do is we're going to use a trapezoid rule, a composite trapezoid rule, to approximate this integral. So delta x is going to be 2 minus 0 over 4. So 2 minus 0 over 4, b minus a over n. So this is going to be 1/2. So on my x-axis, x0 is going to be 0. x4 is going to be 2. Let's see. 1 is like right here, so 1/2 and 3/2. x1, x2, x3. So 1/2, 1, 3/2, 2. So those are my 5 points that I'm going to use when I'm doing this composite trapezoid rule. Basically, add delta x to 0 to get 1/2, add delta x again to get 1, add delta x again to get 3/2, add delta x again to get 2. So those are my 5 points. So I've created 4 subintervals, x0 to x1, x1 to x2, x2 to x3, x3 to x4. So we've got our 4 subintervals. We're going to use our composite trapezoid rule to approximate this integral. Okay, so the composite trapezoid rule says, I'll call it integral from 0 to 2 e to the negative x squared dx equals, or approximately is equal to t4, I'll call it, which is delta x over 2 times f of x0 plus 2 times the summation I equals 1 to 3 f of xi plus f of x4. So this is going to be 1/2 over 2, which is 1 over 4, e to the negative 0 squared plus 2 times e to the negative 1/2 squared plus 2 times e to the negative 3/2 squared plus 2 times e to the negative, whoops, I skipped 1, sorry. Make this a 1 right here, 1 squared, negative 3/2 squared, plus e to the negative 2 squared. So basically just evaluating my function e to the negative x squared at each x value, 0, 1/2, 1, 3/2, 2. And the ones in the middle get a coefficient of 2. So they're all multiplied by 2. I'm going to need somebody to hook me up with a decimal here, but this is going to be, basically e to the 0 is 1. So 1 plus 2 e to the negative 1 over 4 plus 2 e to the negative 1 plus 2 e to the negative 9 over 4 plus e to the negative 4. So what do we get for this answer? .8806. Is that rounded to 4 decimals? Okay, perfect. So the integral from 0 to 2 of e to the negative x squared dx is approximately 0.8806. Cool. Make sense? Awesome. Let's program the trapezoid rule in Matlab. Let's write a function called trapezoid. It's going to take in a function handle that we want to integrate, an upper and a lower bound, a and b, or lower bound, upper bound, and n is going to be the number of subintervals we want to use for trapezoid. So let's create a new function. And we'll call this function trapezoid. Okay, so I need a function to integrate. I need a lower bound and an upper bound, and I need a number of subintervals. This function will implement a composite trapezoid rule for integration based on n. Basically, we need the user to tell us how many subintervals. I guess we could default it to 1 if the user doesn't specify. But we probably won't put in all those checks that we normally put in at the beginning, all the nargin stuff. I'm just going to assume the user is going to specify all of these values. If they didn't, it would actually provide an error because it say a certain thing is undefined. So at least you need F, A, and B, right? But we're going to assume that they also put an N in there. All right, so what we're going to do first is define, let's see, should I call it dx or delta x? What should I call it? Just dx? Okay, we'll say dx equals b minus a over n. So that's my change in x. So change in x is going to be dx. So then our x-axis, we'll call it x, is going to be a colon dx colon b. That's going to be my vector of x values. My vector of x values we should specify f is a function handle provided by the user. A is the lower bound of integration, and B is the upper bound of integration. All right, cool. So I got my x-axis, I got my dx. All I need to do now is basically like add all those terms together, all my function values. Make sure I multiply by 2 on the ones that need to be multiplied by 2. So I'm gonna initialize my integral value to be 0. So int will be the value of the integral of trapezoids. All right, so now let me loop through. Let me define n equals the length of x. So loop through all the way up to n. So for I equals 1 to n plus 1. Oh, there's a little bit of a discrepancy because Matlab can't access x of 0. Matlab starts indexing vectors at 1 instead of 0. So there's a little bit of a discrepancy there from what we wrote down. So instead of doing 0 to n, we have to do 1 to n plus 1. Oh, that's a great question, actually. So let me say m equals length of x. Oh, you're right. Actually, hold up. That's a great question. Yeah, I don't need to do that. N is already defined, and it would be the same thing. You're exactly right. Yeah, we already have n. Thank you. Great question. That's what happens when you do it on the fly. Great question. So n would have been the same thing. Okay. We already have n. Now, let's see. What do we want to do? We want to say if I equals 1 or I equals n plus 1, int is going to equal int plus f of x of I. Else int is going to equal int plus 2 times f of x of I. So we start our integral off at 0, and then we go to I equals 1. And then I add f of x of 1, which for us in our handwritten stuff was x0. So basically f of x0. Now, I equals 2, I go to the else part and I say int equals int plus 2 times f of x of 2, which for us was 2 times f of x of 1, or f of x1. So basically we've done a 1 shift in our index. Now, what's the only thing I have left to do after the for loop is done? I still have to divide or multiply by x delta x over 2. So int equals dx over 2 times int. So I need to not forget to multiply by delta x over 2. And then int should have the appropriate trapezoid value at that point. So that would be our integral, our trapezoid integration approximation. Okay? So if I is 1 or n plus 1, I'm just multiplying the function value by 1 and adding it to what I've already got. If it's between 1 and n plus 1, like 2 to n, I'm going to multiply my function value by 2 and then add it to what I've already got, and then keep going. Okay? Questions? Let's test it on our function that we just did by hand. Let's make sure we get the same thing if we use it on our function that we did by hand. Let's see what happens. So let's save this as trapezoid.m. We'll minimize it, create a new script file. And this is testing our numerical integration functions. So here we're going to say I equals trapezoid of f0 to 4. So I got to define f. I'm going to do CLC clear all. F is going to be a function handle of x, and it's going to be exp of negative x squared. I don't have to vectorize anything, like do x dot square, because I'm not plugging vectors in to my function. So I'm not going to vectorize it, although you could put an x dot squared right there in line 5. Okay, let's see if the value of I, at least the 4 decimal places, matches what we got when we did it. So run, save it as testing Newton Coates 0.8806. Is that the same thing? Look at that. That's awesome. That's awesome. So now you could pretty much integrate any function you wanted to, as long as it's like not discontinuous or anything crazy, mathematically, theoretically. As long as it's going to have a finite value, you could use a Newton Coates formula to approximate that value. Now, whether or not it's going to be really accurate is a different story. That depends on the n that you use and the function that you're integrating and how close it is to an infinite discontinuity and all kind of different, things like that. But or maybe how much oscillation there is in the function. But barring a lot of theoretical considerations, this trapezoid function is going to be able to integrate pretty much anything that could be integrated, a finite value over some interval, as long as there's no like crazy discontinuity or something. Now, it's not the most accurate form of integration. It's the most basic numerical integration. Well, aside from Riemann sums, left, right endpoints, midpoints, stuff like that. Those are pretty basic. But this is the first step towards a more advanced type of numerical integration. Make sense? All right. Questions? Yes. Oh yeah, make the n really large. Yeah, you can try to make it more accurate by making n very large. Yes, it is possible. Yes. However, there are more integration techniques that are a lot better, and you only need 3, 4 function evaluations versus if you had n equals 1,000, that's 1,000 function evaluations, or n equals 1,000,000, that's 1,000,000 function evaluations that your computer has to do, versus some better techniques we're going to talk about Thursday, just 4 function evaluations. That's all you need. So let's go over another interpolating approach. So that was using linear interpolating polynomials. Now let's talk about using a quadratic interpolating function, okay? So part 2 of today is about using quadratic interpolating functions. So part 2 for today, we could use quadratic interpolating functions. And the first one, or the first way we could do this, is to use a single Simpson's 1/3 rule. And we'll show how we get everything. So single Simpson's 1/3 rule. So basically what's going to happen to our function using a single Simpson's 1/3 rule is, say this is our function. Then over this interval AB, we'll call interval AB here. What we're going to do is we're going to take 3 function values, A, B, and we're going to take the midpoint. And what we're going to do is we're going to interpolate those 3 values with a single parabola. Okay, we use our P2 of x basically. So that's going to be some parabola that goes through these 3 points. So integral from a to b f of x dx will be approximately integral from a to b p2 of x, the second interpolating polynomial, through these 3 points. So that would be our quadratic interpolating polynomial. So P2 of x, I'll write it out, but I won't go through the whole integration like we did last time, but P2 of x is equal to f of xa plus f of b, sorry, that should be f of a, f of b minus f of a over b minus a times x minus a, plus, now that complicated coefficient that we had last time was f of b, ooh, let me rethink this. F of a plus, the second one should be f of a plus b over 2 plus, sorry, minus f of a over a plus b over 2 minus a times x minus a plus f of b minus f of a plus b over 2 over b minus a plus b over 2 minus f of a plus b over 2 minus f of a over a plus b over 2 minus a all over b minus a. So basically just using that Newton's divided difference from last time times x minus a plus b over 2. So this is our quadratic Newton interpolating polynomial from last time. Very, very fun to calculate if you recall. So this is our quadratic Newton interpolating polynomial from last time. Now, I'll spare you all the details this time, I suppose. Spare you all the details. And the integral from a to b, p2 of x dx is equal to delta x over 3, so that's where the 1/3 comes from, f of a plus 4 times f of a plus b over 2 plus f of b. So that's our Simpson's 1/3 rule. So this is a single Simpson's 1/3 rule. So this is a single Simpson's 1/3 rule. The 1/3 obviously comes from the fact that there's delta x over 3 out front. Simpsons, where does that come from? Probably somebody's name. Typically where that comes from. Had to be the Simpsons. All right, so notice that a single application of Simpson's rule requires 2 intervals because I'm creating a quadratic polynomial. So if I have a quadratic polynomial, I have to have 3 points. 3 points means I have to have 2 subintervals. And what I'm going to assume is that those intervals are equally spaced. Okay? Therefore, I'm using the midpoint, a plus b over 2. That makes sense? Now, what can we do to make this better than just using a single quadratic function, bless you, over the whole interval ab? Well, we could use a bunch of consecutive 2-interval interpolations of quadratic functions. Okay, so part B to this would be the composite Simpson's 1/3 rule. So part B would be the composite Simpson's 1/3 rule. And that would say, okay, this is really maybe hard to draw, and I probably shouldn't try to draw, but I will. So let's say I want to integrate from a to b. Again, the same, basically the same function we had last time we did composite. So again, what we're going to do is cut this up into a bunch of little subintervals. Okay. Whenever we do a composite Simpson's 1/3 rule, we have to have an even number of subintervals because we want to create a quadratic to interpolate over each successive 2 intervals. So my first quadratic I'll draw in blue here is probably something like this. Actually, let me draw it in yellow. So it would be something like this. So that would be my first quadratic function to interpolate the first 3 points. And then the next 3 points would be a different quadratic function. Maybe something like this. I'll draw in blue. So really the piece that I would use is this blue quadratic piece and this yellow quadratic piece. And then the last one I'll do in red maybe as this quadratic function. Maybe something like that. So I'd use this red quadratic piece. So basically what I'm going to do is find the area over each little successive 2 subintervals. Add all those together. So again, we'll start out x0, x1, xn minus 1, xn. Of course, for Matlab, we're going to have to do a shift of our indices by 1 because MATLAB can't say x of 0. It always accesses vectors by starting at 1, right? The indexing starts at 1 for vectors in MATLAB. So over, let's say delta x again is going to be b minus a over n. Xi is going to be x0 plus I delta x. But now n must be even. N must be even if we're just going to apply Simpson's 1/3 rule over the whole interval. So that's a requirement of Simpson's 1/3 rule. You have to have an even number of subintervals so you can add, or so you can interpolate 3 points over each 2 subintervals next to each other. All right, so let's focus on interval xi to xi plus 2. So focus on the interval xi to xi plus 2. So the integral from xi to xi plus 2 f of x dx is going to be approximately delta x over 3 times f of xi plus 2 times f of xi plus 1. Sorry, 4. That's a 4. Plus f of xi plus 2. So I would basically be applying a single Simpson's 1/3 rule over that interval xi to xi plus 2. So you could think of this as like xi, and this is xi plus 2. That would give us the area of that single parabola integrated over the interval xi to xi plus 2. Okay, that makes sense? So then the total integral from a to b, f of x dx will be approximately delta x over 3 f of x0 plus 4 f of x1 plus f of x2 plus delta x over 3 times f of x2 plus 4 f of x3 plus f of x4. Plus delta x over 3 f of x4 plus 4 f of x5 plus f of x6 plus delta x over 3 f of x n minus 2 plus 4 f of x n minus 1 plus f of x n. course, we could write out each interval. This is the interval x0 to x2. This is the interval x2 to x4. This is the interval x4 to x6. And then this is the interval xn minus 2 to xn. So I'm using a quadratic over successive 2 subinterval. And adding those areas together. Now I can factor out delta x over 3 and say that this would be delta x over 3 times f of x0 plus 4 times f of x1 plus 2f of x2 plus 4f of x3 plus 2f of x5, 4 plus 4f of x5 plus dot dot dot. And we get out to 2f of xn minus 2 plus 4f of xn minus 1 plus f of xn. So basically it alternates starting in the middle from x1 to xn minus 1, 4, 2, 4, 2, 4, 2, 4, 2. And then the second to last term is always a 4. And then the outer terms, 0 and n, are going to be a multiplier of 1. Okay. So for us right here, doing it by hand, basically if you're in the middle and you're an odd index, like 1, 3, 5, or n minus 1, you get a 4 multiplied on. And if you're in the middle and you're an even index, like 2, 4, 6, 8, dot, 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 n minus 2, you get a multiplier of 2. Well, in Matlab, we're going to have to shift that over 1. So basically, we're going to have odd indices getting 1, 2, 2, 2, 2, 1, and even indices are going to get 4s, everything in the middle. So Matlab's going to have to shift it over 1 index. So basically, in Matlab, just make a note. If I equals 1 or n plus 1, coefficient equals 1. If I is even, coefficient will equal 4. And if, I'll basically just say else, the coefficient is going to be 2. Right, because in Matlab, we're going to have to shift over our indices starting at 1 instead of 0. So that's how we're going to code it in Matlab. The mathematical way to write this, I'm actually not going to just like do it for the sake of doing it. Basically, I have to create an odd index and an even index by saying 2i plus 1 or 2i minus 1. So I'm not going to worry about that. But just know that in the middle it alternates 4, 2, 4, 2, 4, 2, 4, 2, 2, 2. The second to last one's always 4, and then 1. So the outer terms have coefficients of 1. Inner terms alternate 4, 2, 4, 2, 4, 2, 4. All right, let's look at our example, e to the negative x squared from 0 to 2, but now use the Simpson's 1/3 rule, n equals 4. Okay. So example, use our Simpson's 1/3 rule to approximate integral from 0 to 2 e to the negative x squared dx. And we're going to use n equals 4. So that's a composite Simpson's 1/3 rule if n equals 4. If n equals 2, it's a single Simpson's 1/3 rule. Okay, so composite is anything greater than 2, and single for Simpsons is n equals 2. So solution, delta x is going to be 2 minus 0 over 4, which is 1/2. And then our x-axis stays the same, 0 to 2. 1's in the middle, 1/2, 3/2, x0, x1, x2, x3, x4. So our integral from 0 to 2, e to the negative x squared dx, is approximately, I'm going to call it S4, which will be delta x over 3 times f of x0 plus 4f of x1 plus 2f of x2 plus 4f of x3 plus f of x4. So that's going to be 1 over 6 times e to the negative 0 squared plus 4 times e to the negative 1/2 squared plus 2 times 2 times e to the negative 1 squared plus 4 times e to the negative 3/2 squared plus e to the negative 2 squared. So that's 1 over 6. E to the 0 is 1 plus 4 e to the negative 1/4 plus 2 e to the negative 1 plus 4 e to the negative 9/2 plus e to the negative 4. And as soon as somebody gets it, let me know what that is to 4 decimal places. Okay, 0.8189. That's cool. Okay, 8190 if it rounds. Okay. So 0.8190 if we round to 4 decimal places. All right, cool. All right, let's program it in Matlab. Yes, we have a question actually. Yeah, oh yeah. Should be 4th. Oh, yes, 4th there. Thank you. You said 0.8818. Okay. Yeah, I was thinking I was pretty far off from our trapezoid, but I mean, trapezoid isn't typically as good as Simpson, so I wasn't red flagging it super hard, but it was a little bit of a red flag. Thank you. Yeah, it should have been -9/4 there. That's my bad. It is off from trapezoid. Trapezoid was 0.8806. Simpson's is 0.8818. So I wonder which one's closer. We'll see. We'll see in a minute. Let's code up the Simpson's 1/3 rule. Let's code up the Simpson's 1/3 rule. Go back to Matlab. Create a new function file. Wonder if I could just copy my trapezoid. Let me do that instead. I'll take trapezoid, copy it. I'm gonna call it Simp's third. So I have to change some stuff, but it's gonna be roughly the same skeleton. So might as well just copy this here. So I gotta change the name, first of all. I gotta change the name to Simp's third. Simp's third. FAB are gonna be the same. The description needs to change. This will implement a composite Simp's third rule. Simpson's 1/3 rule for integration based on n. N must be even. I'm not going to put a check in there to make sure that's okay. We probably should, but I'm not going to. This part, lines 8 through 11, are all the same. What changes now is our loop. So our loop, if it's the first point or the last point, we're still good, right? If it's the first point or last point, it still needs a coefficient of 1. Now, in the middle, I should say else if something. And I think it was else if I is even, so basically I mod 2 is even, give it a coefficient of 4, else give it a coefficient of 2. So let's just make sure I'm using that mod operator correctly. The modulo of a number returns the remainder when you divide the first number by the second number. So if I divide I by 2 and I get 0, that means it's an even number, right? The remainder is 0, that's an even number. So let's just make sure I'm using that modulo correctly. So mod 8 comma 2 should give me 0. Whoops. I meant mod, yes. So that seems to be what I'm using. So if I did 5 mod 2, I should get 1. If I did 5 mod 5, I should get 0. If I do 5 mod 7, I should get 5. Okay, so we're using it correctly. The first number is the number you're dividing by the second number. So modulo means take the remainder of the first number divided by the second number. So if I'm dividing I by 2 and I get a remainder of 0, that means I've got an even number. And I said in Matlab that my even indices are going to be the coefficients, or going to be when I get a coefficient of 4 on my function value. Because we had a 1 shift in our index. Initially, it was all the odd coefficients. Well, here it's all the even coefficients. For f of x sub even number, I should multiply that function value by 4 and add it to what I've already got. The last thing is to change line 24 to delta x over 3. And we should be good to go. As long as people put in an even number of subintervals, we should be good. Okay, so save that. Simp's third. Make sure everything's good. So let's go to our testing script. And let's change the name in line 7 to be iTrap. And then Simps equals Simps third of f 0, 2, 4. And run it. Hey, look at that. 0.8818, just like we got after we corrected the error mistake. All right, man, that's cool. Nailing this stuff. So we now know how to tell our computer how to integrate numerically. At least definite integrals, right? This is how we do definite integrals. How do you do an indefinite integral in a computer? It's a much harder thing to figure out. Obviously, some people have figured it out and sold it, but how do you do an indefinite integral in a computer? It's a much harder thing to figure out. Okay, questions? Anybody? We got a question, yeah. Oh yeah, great question. So like some functions have no antiderivative, and you can't use the fundamental theorem of calculus. However, like if you were to graph e to the negative x squared, you could see that over the interval 0 to 2, it's a finite value. Okay, that we're not really talking about all these error bounds on, okay, how many n's would you need to use if your function's continuous? How many n or what size n would you need to make sure your error is a certain like within a certain amount of the actual integral itself? Okay, so we're not discussing all the error approximations or the error estimates and stuff like that, but that's also a side discussion to have when you're doing these numerical integrations. So yeah, if you make n large enough and it is a finite value, you're going to approach that actual value if you make n large enough. Basically, what we do to compare in our case, like we're just learning, what we do is we say, okay, what does Matlab say this function should be integrating to? So in Matlab, there's a built-in integral function or integral evaluator. We could say I Matlab equals quad f02. I have to vectorize it to use quad. So vectorize it. So I Matlab says 0.8821. And we would take that to be the quote unquote true value. It's just a much better numerical approximation. And some theory that we're not really discussing would tell us how close it actually is to the real value based on the scheme that they used and all the things that go into that scheme. Okay. So that's a built-in MATLAB function. It's using some type of quadrature. We're actually going to talk about quadrature next time, Gaussian quadrature. And this is a much more advanced type of what we're going to do next time. But they use a much more accurate numerical technique, and we would call that the true value as far as we're concerned. So we could say the true value is probably like 0.8821. Our Simpsons got 0.8818, and our Trapezoid got 0.8806. So we can see Simpsons is closer to the quote-unquote true value, or the better numerical approximation given by MATLAB itself. Okay, that's a great question. How do we know if it's getting there or not? And that's actually a lot of calculus. We could do more calculus to know, okay, is this scheme going to converge to the actual value if I increase n to be larger and larger? And it will, if the function satisfies certain criteria, being continuous, stuff like that. Great question. Other questions? All right, what if you wanted to use a better scheme or a better formula than trapezoid, but you had an odd number of subintervals? Okay, if you had an odd number of subintervals, but you wanted to use something better than trapezoid, what you could do is create a cubic polynomial over 4 points. So basically the last 3 subintervals, you could create a cubic polynomial, use that for the last 3 subintervals, and then use Simpson's for the first even number of subintervals. Okay, now let's say you had 7 subintervals, n equals 7, over subintervals 1 and 2, subintervals 3 and 4. you could do Simpson's 1/3 rule. And then over subintervals 5, 6, and 7, you would create a cubic polynomial and use a Simpson's rule called Simpson's 3/8 rule. So you can actually use 3 subintervals to create a cubic polynomial that goes through 4 points, and that's called Simpson's 3/8 rule. You can Google that. Actually, I guess we could Google it here, see what Google says about Simpson's 3/8 rule. So Simpson's 3/8 rule. There's ours, Simpson's 1/3 rule right there. Composite, Simpson's 3rd rule. Simpson's 3/8 rule, there it is. So it's kind of nasty. It's got a 3/8 times delta x or h. And so then that would be our approach. Does that make sense? So you could use Simpson's 3/8 rule in conjunction with Simpson's 1/3 rule if you had an odd number of subintervals that you want to use for a higher accuracy than trapezoid. If you wanted to do a composite formula like this. This is called Newton Coates formulas. These are formulas derived from Newton Interpolating Polynomials. We call them Newton Coates formulas. Newton Coates Numerical Integrating Formula. Okay, cool. I guess that's it for today as far as material goes, unless there are any other questions. Any questions online or anything? Otherwise, I'll just stop the recording here, take the roll, and work on Matlab problems. Okay, see you.